Dear students, how are you all? I really hope you had a very good lunch. Thank you for coming back. Welcome once again to the 5th edition of Annual Nepal AI School, organized by Nepal Applied Mathematics and Informatics Institute for Research, NAM. So today we're moving towards our second lecture. So we have, I think.
So my full name is Haitz, Sáez de Ocáriz, Borde, and just for short, Ocáriz is fine. Yeah. So.
Thank you so much. So he is a PhD researcher at the University of Oxford, UK, and he has been working on geometric deep learning and generative models. So it's going to be a 1-hour lecture, and I request you all to have a good attention, and we'll really appreciate the questionings that will be followed. Thank you so much.
Okay. Hi guys. So basically we're going to be talking about geometric priors, and I'm going to be building a bit on what Michael has explained in the previous lectures. Normally this at Oxford is a couple lectures, and also today we were running a bit late, right? And we only have an hour to go over it, so I kind of tried to condense it into just 1 hour. So we're going to overview the main concepts. But yeah, I would encourage people later to kind of dive deeper, maybe into the geometric deep learning book. There's also the mathematical background. I don't know if everyone got access to it, but it has like more kind of mathematically principled definitions for what's a group, what's a vector space, stuff like that we're going to be discussing, or kind of discussing quite briefly, or without going into that much of a mathematical detail. So I would encourage people, if they can have the mathematical background notes, so they are more up to date with everything. So, okay, basically, what's a geometric prior? So a geometric prior is a type of inductive bias. And basically an inductive bias is a set of assumptions that we use to constrain our model. And the idea is that apart from learning from data, we also want to have like maybe you have some additional knowledge that we can leverage to generalize to unseen data. So geometric priors are a type of inductive bias, and then we can incorporate specifically assumptions about the geometry of the data and also of the underlying domain. So yeah, basically something that helps us kind of tackle this problem that Michael has already discussed before. So we have kind of the curse of dimensionality. And the problem is that as we increase the number of dimensions in which our data lives, we need more and more data to have an equivalent amount of coverage and to get the same kind of approximation error. And this increases exponentially, so this is a bit of a problem, right? It's not like I add another dimension, I need twice as much data. No, this growth is actually exponential. So can we do a bit better by leveraging these geometric notions that we call geometric priors and using them as kind of an inductive bias to improve our generalization? So basically, these kind of biases are going to help us restrict the hypothesis class. So basically, kind of the hypothesis class is the set of functions that neural networks can represent, given their architecture, parameters, and activation functions. And kind of the idea is, going back to this picture that we've seen briefly before, is that we kind of want to restrict the kind of functions that we can sample according to some additional knowledge. So not just kind of the distribution that we could sample from according to the data alone, according to data samples, but we know sometimes that our signal is in some specific domain that must satisfy some properties. And in particular, we've spoken quite a lot about symmetries, right? So we want to sample functions that accommodate or respect these kind of symmetries. And we know that our solution needs to be one function from this hypothesis class. So in principle, as long as kind of our assumptions about symmetry are correct, we are not making our approximation worse. We're just kind of restricting the functions that we are sampling from to the correct class. Okay. So basically, we're going to talk about the domain, the geometric domain, the signals, and the functions that we are trying to learn. So we say that our data sample, right, is kind of a signal on a geometric domain, and kind of the space of signals, we use this kind of math style X on the geometric domain. So we have, for instance, we can have a grid, right, for images, and then we have like RGB signal, and that's our data. And then we have a function that takes this data that lives on the geometry, and then we are trying to learn a function, for instance, trying to classify an image, right? So, okay, so let's focus first on geometric domains. So we have a signal, right? And this signal is a C-valued function on the geometric domain. So basically it maps from the domain, which is some set. We can discuss this more later, but maybe we have like a collection of elements with some additional structure, and then we map this to the space C. So basically the domain omega often doesn't have a vector space structure, so this means that we don't necessarily need to be able to scale and add elements of the geometric domain, but then we have our signal which maps that geometric domain to a vector space, right? Which normally is like some channels. So in the vector space we can scale and add signals, and then basically the mapping, in the case of an image, I think it's easier to understand when we just look at a practical example. So for instance, we have our geometric domain, which is this grid-like structure, so we can think each node is a pixel, so the location in the XY plane, and for each pixel we assign an RGB value. So then when we have our image lives on this geometric domain, and then the collection of the pixel values would generate our image. Okay, then we can have like more complicated domains, so we can have a manifold, which basically locally resembles Euclidean space, but we can think of it, let's just kind of at a high level think of some kind of surface, in this case kind of embedded in three-dimensional Euclidean space, and at each point in the surface we can also define an RGB color. But this doesn't necessarily need to be the case. Maybe our manifold is a sphere, and we have kind of the value on the sphere is, for instance, the pressure on the surface of the Earth, right? So here again, we have a mapping from our geometric domain to some kind of vector space. Okay. And then we can have even more fancy structures. So for instance, a molecular graph where our domain is a tuple, so it's basically two sets. The set of vertices or nodes of the graph, and the set of edges or links. Sometimes we also call them links, right? So we have this geometric structure, and then at each, so if we think of this as a molecule and then this as an atom, right? This kind of entry in the geometry maps to some Rm space, and in particular we could have, for instance, we are just trying to assign an atom type, so we can have carbon, nitrogen, oxygen, and this may be a one-hot vector. So for instance, if this node is a carbon, then we would have a vector which is 1, 0, 0, 0, and if this is an oxygen, then we would have everything zeros, and the last entry would be a 1. And we can have m would be the amount of different atoms we can have. Okay, so in general, maybe another intuitive example, our geometric domain may be a point cloud, which is a bare set. So a set is just a collection of elements. It can be a graph in which we have defined a local neighborhood structure, or it could be a mesh, which also has a local metric. We can think of this as a discretization of a manifold as well. And then we can have signals on these different domains. And the idea is that depending on the domain, we may have additional information to kind of better map or better model the signal and the function to the label space. So in this space of signals, as we said, basically we can scale them and add them up. So here we have like two pictures, and we can scale them and add them up together, even though maybe in the actual geometric domain these operations are not well defined. So that's kind of a distinction between the two types of spaces, the space, like kind of the geometric space, and then the space of signals. So we can also define inner products in general, so this allows us, for instance, to measure angles. And we can add different types of structures, so we can have like a normed space, a metric space, an inner product space to kind of add additional structure on top of the underlying set. And then we won't go into much detail here, but we can also use the domain as a signal itself. So for instance, we can, we're gonna have a look at this later, but we can have like an adjacency matrix, which basically tells you about the connectivity structure of the graph, right, of the underlying geometry. And we can also have like metric tensors. These are used in Riemannian geometry and Riemannian manifolds. And we can potentially use those also. So then we have the label function. So we said before, right, before we were mapping the geometry to a C-valued vector space, but we also have label functions that basically map now the space of signals to the space of labels. So this is kind of the third component that we're discussing. And Michael showed like a very similar picture before. So in this case, for instance, if we look at a molecule and we have a regression task, the domain is, again, the graph, which is a tuple of the vertex set and the edge set. Then we have this signal in Rm, and then our label may be like a scalar, right? A real value that we are trying to regress. In the case of classification of images, we have, again, the grid. I think we've discussed it multiple times, right? So basically we have pixel positions, then we have RGB values at each pixel position, and when we're doing multi-class or multi-label classification, we have like these different labels that we can use. Maybe we have cats, dogs, horses, different classes. In the case of structure prediction, maybe you're trying to segment the image, right? So both the input domain is a grid, then we have the RGB again, and now our labels are also this grid that we are trying to do binary classification on at the pixel level, and we are trying to maybe distinguish between foreground and background, or we could have different segmentations in which we have multiple classes, not just binary classification. Okay, so this is kind of to recap what we've looked at. We have our domain, right, omega. Then we have the mapping to the space of signals, and then we have the function that we are trying to learn. So in the case of images, just to repeat myself, I have the grid, the pixel positions, I have the RGB values at each pixel position, and then I have the function which may be kind of classifying the image. Okay. Now we're gonna discuss a bit symmetry groups. Again, as I mentioned before, in the mathematical background section, there's more on like group theory and stuff like that, which I think is better to read in your own time. But I'm gonna try to give more of a pictorial description of the concept, and hopefully that's enough to motivate the rest of the lecture, at least at that kind of abstract level. Okay, so. For instance, in the case of this snowflake, right, we can see that we can rotate it, right, as you see in the animation, and still looks unchanged, right? It looks the same, has the same overall structure. We could also, for instance, reflect it about the y-axis or reflect it about the x-axis, right, and it would still look the same. And kind of the idea of symmetry is that it's a transformation that leaves the object unchanged. So these are examples of transformations that leave the object unchanged. If we look again at the rotation, right? It looks like exactly the same snowflake. So maybe if we look at a triangle, which is a more simple, right? We are gonna, just for the sake of keeping track of which are the points in the triangle, we have this labeling 1, 2, 3, and then we can apply, for instance, rotations. Right? If we look at the triangle at the high level, it looks exactly the same, and we've seen that we've switched around or rotated these labels. Okay, so this is our rotation, like kind of half a circle rotation, 120 degrees. We can also do our reflection, so the same thing I mentioned with the snowflake, right? And kind of the triangle looks exactly the same. And now we can construct something called like a Cayley diagram of different transformations. So these are kind of 120 degree rotations, and we can see how we revert to the original triangle configuration, and we can just directly do 120 degrees twice, right? So we can compose these operations. And then we can also take inverses. So we could go from this configuration to the original configuration. We don't necessarily need to go always clockwise, right? And then we can have our reflections, and then we end up with this kind of overall representation, right? We have this Cayley graph, and then we also have a table. So this basically tells you, it's a way of looking at all the possible rotations, reflections that we can compose together and seeing what they result. So for instance, if you don't do anything, you have like the identity operation, you do it twice, you still get the identity. But for instance, if you do 2 rotations clockwise and then another rotation, then it's equivalent to not applying any transformation to the triangle in the first place, because basically you just go twice, another time, and it's the same as the identity operation, right? So this is basically a way of quantifying all the different transformations that we can look at that respect the symmetry of the triangle. And we can get into very complicated tables and Cayley graphs depending on the structure that we are trying to model. So then we have groups, right? So kind of group is a kind of an algebraic abstraction of this concept that we've looked at in terms of pictures. But basically it's a set, right? So we have like a collection of elements and then a binary operation. And the binary operation is some transformation that must satisfy the group axioms. So when you look at it this way, it looks a bit abstract, but again, I try to kind of show examples. The basic idea is that you need to satisfy these 3 axioms: associativity, identity, and inverse. So and from this it follows the closure. Kind of in high level terms is that I can apply, so I can kind of combine. So first, maybe let's look at the binary operation. You take like 2 elements of the group, and it returns another element of the group, and then you should be able to combine them irrespective of order. So don't confuse this with commutativity, because this is a special type of group, abelian groups. Then you also need to have the identity. So basically, if you combine the identity with another element of the group, you get the element of the group itself, and then an inverse. So this is similar, for instance, the inverse is similar to when we were looking at the graph, right? Going, rotating clockwise, and then the inverse would be rotating anti-clockwise, and then we would recover, if we compose these 2 operations, we would just recover the identity. So basically, these rules that look quite a bit abstract when we just define them this way are kind of grounded in this intuition of symmetry that we've discussed before, and it's a way of formalizing these different transformations and the properties that they must satisfy. And then we can have finite groups, infinite groups, discrete and continuous groups, which I won't discuss into much detail. But I do want to mention this concept, which is quite interesting. So basically, we can find equivalent groups. So in this case, when we were doing the labeling, right, we had this different 1, 2, 3, right? So we can relate this to the permutation group. So you can find groups that satisfy the same transformations or the same algebraic properties and symmetries, but represent them with different types of structures. So in this case, we just have these order sets, and we can find permutations of the numbers, and this correspond to actually rotating the triangle. So we call this group isomorphisms. And again, I won't go into much detail, but I would encourage people to look at the mathematical background where everything is kind of discussed more step by step. But kind of the overall takeaway here is that we have some underlying symmetry, some transformations that we can apply, and we can find relations between different groups that seemingly are unrelated and find equivalences when we abstract them away. And we call this group isomorphisms. And there's like a lot of types of groups, which I'm just mentioning here. So for example, like a permutation group, where basically we reorder elements of a set. In general, we just kind of shuffle them around. So this is particularly important in the case of graph neural networks, which I think will pop up later So both in lectures and also in terms of the notebooks, we have like cyclic groups, and then there's this kind of long list of groups that people can look at if they are interested in. But so now basically we've looked at this kind of symmetries. So these symmetries may be satisfied by our domain, and now we're gonna have a look at these signals on that domain. So this, as I said, it looks quite abstract, but in terms of geometric deep learning and deep learning, we are more interested in group actions and how this affect the representations. So we have this thing called a left group action. So basically, we can define a mapping, alpha, that takes an element of a group, and then an element of a set, and it returns another element of the set. Again, we have like this kind of properties that we must satisfy, but I think the easiest way of thinking about this is in terms of pictures again. Because the mathematical abstractions, if it's the first thing you look at, it can be a bit hard. But if we look at this kind of group actions and taking elements of the set and getting another element of the set, let's look at, for instance, a point in the plane. Right? We have a set of points, so different points on the plane. And then we have a group action, which maybe is a rotation, and then it gives us another point on the plane. So this is what we were discussing, right? So we have the rotation, which is just as we looked before. We had a look before with triangles, right? 120 degrees rotation. Then here we have a theta rotation of this many degrees. We take the point, we rotate it, and we get another element of the set. We can also do the same thing, but at the image level, right? We have the original image, which maybe is the cat here at the back. We apply the same rotation, and we get another element of the set, which is the rotated cat. And then we can have the same thing with vector fields. So the idea is that we have some signal or some element of a set, and then we apply some kind of transformation that returns another element of the set. And that's kind of an overview of what's a group action, very loosely speaking. So in the case of graphs, for instance, this is our domain, right? So it's an abstract object. We have like some nodes and some connectivity. And then we assign an arbitrary labeling of the nodes. So I think Michael already discussed this before as well. And based on this arbitrary ordering, we have a way in which we organize the adjacency matrix and the feature matrix. So here n is the number of nodes in the graph, and this is the feature dimension, like the feature dimensionality for each node, and we get this matrix. So we can apply permutations to this graph. We can apply permutations to this graph and kind of reshuffle the number that we assign to each graph, and in such a case, we will change the... Yeah, okay, sorry, I was missing the animation. So basically, if we have this feature, right, and we permute the nodes, so basically we shuffle the order in which they are presented, then the corresponding feature matrix and adjacency matrix also needs to change. So this is an underlying symmetry or property that we want to satisfy when we actually work on our graph neural networks. And then lastly, we have the functions, right, that are going to take these signals, and we're going to try to model the functions and get maybe do regression, do classification, and we're trying to learn this kind of mapping. So then we're going to look into the symmetry in terms of learning. So we've seen that we can have symmetry in terms of the domain, the geometric domain. We can have symmetry in terms of the signals, and now we're going to look at symmetry in terms of learning. So we can have some transformations. This is like function composition, right? We have a label function that maps from the space of signals to the space of labels. This is the mapping. And then in the case of the labels, we have 1 to k labels. So this is like multi-class classification. And then we can define some transformation G that when we take the space of signals and transform it according to G and then apply F, we always get back to the same Y. So there's asymmetry in terms of the input to the function. So again, maybe we can look at it in terms of pictures, right? So in terms of the label function, we have this input, which maybe is the letter A. We can rotate it in different ways, but it should always be classified as A. In this case, A, in practically speaking in machine learning, maybe we use like a label, which is 1 and 0, right? So irrespective of how we rotated A, we should still map to the same label. So this rotation would amount to the G transformation here, right? So basically F, irrespective of whether you give me the original A or a rotated version of A, should map to the same space. So this is the intuition. If we have B, the same. We can have rotations or some other transformations and always map to the same point. And in general, we can have like very complicated symmetries or transformations that we want to be invariant to, which would be, for instance, here is represented with A rotated in different ways, having different font sizes and different styles, right? And the same with B. And in general, if we know all the symmetries of the program, then we only need a sample of each, and we can just learn the assignment to the class directly. But more generally, in most programs, we actually don't know most of the symmetries, so we kind of try to find a balance between the symmetries that we know and the symmetries that we can learn from data. And then we can have other types of symmetries which are not maybe that typical to look at, but maybe we can have symmetries of the weights. So this is just an example. So basically imagine we have the mapping function, which is a parametric model, such as a neural network that takes an element from the signal space and then weight configuration. So this would be like basically the weights of our neural networks, and it maps to the space of labels. And then we can look at a transformation, H, that basically shuffles in some way the weights, right? Or I get another weight configuration that results in the same neural network output given the input. So basically it's another type of symmetry, right? How can I have some transformation of the weights that with the same input give me the same output? So this could be, for instance, if we have like this two hidden activations, if we shuffle them or swap them instead, right, we would get still the same output and respecting all the weight connectivities. So there's a symmetry here, right? So this would be symmetry in the terms of the weights of the neural network or our parametric model. And the transformation H would be swapping these two representations. Okay, about invariance and equivariance. So we've spoken about basically these symmetries, transformations that we want to respect, be invariant to, right? So now we're going to try to formalize it mathematically, and we're going to talk first about equivariance. So again, we have a diagram similar to the one we had before, and then we have a left group action here. So basically, in the case of equivariance, right, we have this subscript 1 and 2, just because basically this action operates in the space of input signals, and this one on the space of output signals. But kind of the idea is that if I apply this transformation to the input, it's equivalent to just passing the original input to the function and applying the transformation after. So I'll try to go slowly. So basically imagine I have my space of signals, and so this is the whole space, right? I would take like a sample, and I pass it through the function, and I get a given prediction. I can apply the transformation to the space of predictions and get here, but there's another path that I can follow in general, which is going from X, applying first the transformation, then inputting that to the function, and I would get to the same solution. So that's equivariance. Basically, if I transform the input in some way, and pass it through the function, should be equivalent to passing the original input through the function and applying the transformation after. And then I have invariance, which is a specific type of equivariance in which we basically collapse this path here, right? We collapse it, and if we see it in terms of the diagram, basically there's some kind of transformation in the original input space that when I pass it through the function gives me exactly the same output. So I'm invariant to the transformation. So going back to the triangle, right? When we rotate it, we applied this transformation, it looked the same. So it would be something similar in the sense that we have some input, we apply a transformation, but the function that then is going to return the output completely kind of doesn't care about this transformation, it gives me the same output. So maybe let's look at examples again, because it's easier. So in the case of convolutional neural networks, what we do is we have some input image. In this case, it's just a grayscale image of a 3, right? And then we apply convolution over the image with some filter. And this is the activation that we get as a result. So if we shift the input, the activation looks like the original transformation shifted. So this is going back to what we had before, right? The input here, let's think of it as a 3. The transformation is shifting the 3 or translating the 3 to the right. So we can translate it, then apply the filter, and we get to the same result as applying the transformation and then translating it. So if we look at the convolutional neural network, we have the 3, the kernel, and then when we shift the image, we get the output, right? So this is basically the equivalent of the graph that I just showed, but in the case of images, which is maybe easier to see. So we have the 3, we apply the kernel, we get the activation, and then we can shift it back to the, or translate it to the left. But this is equivalent to first translating it to the left, then applying the filter, and then getting the activation, right? So we are basically equivariant to translations. Okay. Now, in general, CNNs, or this operation, is equivalent to translations, right? Which is basically moving left to right and top to bottom. But it's not equivariant. For instance, we can see here in this animation to rotations. So if our input is rotating about this kind of, just think of an axis going here, we are rotating about that axis. We can see that the feature map, when we have the stabilized version, so basically this is kind of fixing so imagine if we fix our axis here and rotate with the actual input. So this is kind of the stabilized version of this feature map. We can see that as we rotate, actually the activations look different. So what does this mean? This means it's not equivariant to rotations. But there's rotation equivariant CNNs. So basically we can engineer some kind of smart way of dealing with the filters, so that when we actually rotate, we have the same property as we had before with translation, in which our activation looks the same, despite rotating the input, right? So we have this equivariance with respect to rotations. So in general, we can look at different symmetries that we want to satisfy and engineer our neural networks to respect the symmetries. So for the examples of equivariance in different domains, we can have, for instance, in a grid, we have translation. So this was the example with the 3. In the case of the sphere, we have SO3. So maybe we are trying to get points on the sphere, right, by applying rotations. And in the case of manifolds, we have like more complicated structures. But basically, the idea is that we can engineer different neural networks that are equivariant to different groups and respect this kind of feature transformations. So we're going to try to converge in the end to the geometric deep learning blueprint. And right now what we have is we have these functions, right? We can define these layers or these transformations that are G-equivariant and compose them together. And that way, at the end, we're going to engineer or we're going to add another layer which is G-invariant. So in general, we are going to have internal representations which are G-equivariant. Compose them together, we are also going to see that we are going to add non-linearities. And then by composing these functions, so think of them as kind of in the neural network, we have multiple layers, so that's equivalent to function composition. We're just going to restrict our layers to satisfy this G-equivariance, add non-linearities, and then a G-invariant layer at the end. And we are going to see how this actually lets us construct more expressive overall invariant functions. So this is kind of what we've seen so far in terms of the geometric deep learning blueprint, but we're going to add more detail later. So kind of the takeaways of the beginning of the talk is that symmetries are transformations that leave an object invariant. So basically the object doesn't change despite the transformation. in general, in ML, we care about symmetries in terms of the label function, because in reality, this is what we are actually modeling with our neural network. We've seen there's this mapping, or which we kind of argue more in a theoretical way. We have the domain, the signal, right? We have like that mapping, but in reality, what we want to learn or parameterize by our neural network is the mapping from the space of signals or data samples to the labels, right? So we want to learn to regress a property from a graph. We want to classify an image, etc. So that would be the label function. Then in geometric deep learning, we care about symmetries of a geometric domain in which the inputs to our neural network live. So in the case, again, going back to the example, we are going to leverage this to get better neural networks by looking at what are the symmetries of, for instance, in the case of images, translations. So basically then we also discussed equivariance, right? So this will help us engineer better layers. And then we saw that invariance is a specific type of equivariance in which basically the transformation that we apply to the input leaves the output of the function unchanged. So for instance, if we look at the CNN as well, maybe we are trying to classify a cat, right? We can translate the position of the cat on the image, but the label should always be cat, right? So the overall classifier should be invariant to the position of the cat. Okay, maybe does anyone have any questions so far?
Hello.
Hi.
So my question is that any other different priors can be used for instead of the geometric symmetries for different architectures of the neural networks?
Sorry, can you repeat the question?
So can we use different priors other than symmetries for architectures of the neural networks?
Yes, so in general you can use different types of priors or inductive biases, but in geometric deep learning we focus on geometric priors. But you can have, for instance, I don't know, some kind of prior over, if you are trying to model a probability distribution, you can assume that the prior of the probability distribution, so this is related to Bayes' rule, right? We can have like some prior on the underlying probability and then update your estimation, but based on that prior, but that's a kind of at the probability level. Here we're looking at geometry in general, because geometric deep learning, so geometric priors. But you can have other types of inductive biases.
Thank you.
Okay.
Hi, my question is, so we tried to use group theory to define symmetry and transformation. So what if why do you need inverses and identity element? And is it also possible to use the semi-groups and just with lesser operations and still be able to define transformations?
So I'm sure there's some smart way of generalizing these concepts to, I don't know, semi-groups or other kind of structures. But in general here, what we are trying to do, the reason we're talking about this is because we want to restrict the hypothesis class, right? We're trying to generate in general like overall invariant functions to some kind of underlying group transformation, and then we're going to look at it later, but we're going to look at these equivariant transformations, compose them with nonlinearities to get like a hypothesis class of invariant functions, and that's how we are talking about the groups. So in general, this is kind of, for instance, like having an inverse or an identity is just kind of part of the axioms of what defines a group. I'm sure there's some way of generalizing to different things. So there's like a lot of machine learning papers. Maybe if you are looking at metrics, you can normally people use metrics, right? But you can also use quasi-metrics. You can use pseudo-metrics and kind of make fancier algorithms for some specific class of problems. that use some kind of variation of different algebraic structures. I'm sure there's some way of generalizing from groups to other more fancier, less standard structures, if that makes sense. But here we're just kind of trying to look at the overall picture, at the most general way of describing different transformations on data, and kind of seeing how this results in the geometric deep learning grouping, and how we can explain the most kind of different architectures, right? But yeah, I'm sure there's some kind of way of doing something smart and more complicated. Okay, maybe I'll move on to the next part. So next we're gonna talk about scale separation. So we can look at scale separation, for instance, in physics. So when we are at the particle level, for instance, right, maybe we can model the kinetic energy of each particle, right? So basically, we can look at the kinetic energy of each particle in a fluid and try to model it at that scale. But in general, we don't look at it this way. Maybe we just model the temperature. So basically, where I'm trying to get at is that depending on the resolution that we are trying to solve our problem, so we're trying to solve a problem, and then we are trying to solve a problem at a given resolution, we are going to have this scale separation. We are going to model in physics, and possibly as well in machine learning, the problem according to a set of equations, right? So again, if we look at this kind of, maybe at some fluid on top of at some fluid, for instance, like air on the kind of planet Earth, probably we use Navier-Stokes equations, right? We don't look at the kind of kinetic energy or the trajectory of each particle. And then when we are actually trying to model, for instance, the rotation of different planets around the sun, we don't actually pay attention to the different kind of fluid flows on top of the Earth. We just kind of model the planet as a point mass. So kind of the takeaway is that we can kind of have this sense of compositionality and scale separation in which we use different laws, different equations to model different phenomena at different scales. And sometimes kind of using the same, if you try to use the Navier-Stokes equations at kind of the particle level, it doesn't work because it assumes the fluid is a fluid, it doesn't model each particle, right? So kind of the takeaway here is that we have this sense of compositionality or scale separation in which we can look at different problems at different resolutions, and neural networks internally do something similar. So we're trying to motivate what happens, for instance, in convolutional neural networks. So there's like this field of interpretability, for instance, that looks at different activations. And what the neural network is doing metaphorically is something very similar to this scale separation. So the first few filters in convolutional neural networks basically look at low-level features, maybe at edges, try to detect edges, circles, and stuff like that. And then these activations are passed on to other downstream layers, which look at more complicated structures. So basically these substructures are composed to get more complicated structures, so maybe you can compose different edges into an eye, right, at intermediate activations. And then these activations are passed on to deeper layers that then end up being able to detect faces, a nose, a mouth, right? So we have this idea again of scale separation similar to physics and compositionality inside neural networks. And we've observed that we don't need to handcraft this kind of structure by just composing layers and then training it by a gradient descent. The neural network by itself finds this is the kind of the best representation to try to represent the data and learn the label function. So now we can talk about different types of scales, right? So for instance, if I can have, remember we are trying to battle the curse of dimensionality, right? So if we have a very fine-grained input, right, that means the dimension is very high. So for instance, if I have an image which is 1024 by 1024, that has much higher dimensions than a coarser image, which is, I don't know, 128 by 128. Now, we need to be careful here because an easy way or naive way of kind of reducing the dimensionality is just scale down the image, right? And that may work depending on kind of the label function that we are trying to model. So for instance, when we have this when the label function depends mainly on kind of the core structure or the low frequency of the image, that's okay. It's okay to reduce the input grid. So here, I don't know if it's easy to see, but basically the omega has a tilde, which would have, basically it's just a coarser grid. So I put an image here. Basically imagine here the domain has like a lot of entries or a lot of pixels, and here we have a coarser domain. As long as we are modeling a label function that doesn't really care about the high frequency detail, for instance, a beach, as long as we see it's kind of, okay, there's a bit of blue here, there's a bit of sand, we don't need to look at the trees or at the sand grains to know it's a beach, right? And the same happens, for instance, with a mountain. I can know this is a mountain just by the kind of the color gradient, seeing this peak here. I don't need to see the specific rocks, the specific leaves of the tree. So that's an easy way of kind of reducing the dimensionality, right? And hopefully, if we have like coarser images, we need less data samples to model the function. But there's a catch, right? This doesn't always apply. So we need to be careful. So for instance, if I have here some samples from MNIST, which is a very famous data set for a handwritten digit classification, if I actually blur out the image, so kind of you drop your glasses, now you cannot see the actual, you cannot label this, right? You cannot distinguish. So it's going to be very dependent on the actual function. As we've seen, here it's more about kind of the color gradient, the overall low frequency structure, whereas here, to be able to distinguish digits, we actually need the high frequency, and there's a minimum resolution or a minimum grid that we need to actually represent this information. So there's some other cases in which we can try to reduce the dimensionality. Maybe if we are trying to classify textures, they actually doesn't matter the overall global structure, right? So we can look at patches. If I'm trying to classify this as being brick or glass, I can just look at a local patch, and that's enough, right, to kind of get the correct label. So this also reduces a lot the dimensionality, because basically the dimensionality is proportional to the patch size. So here also the curse of dimensionality can be avoided, but again, this is not a general, it's not true in general, right? So I could have some 3D global structure, for instance a rabbit, a horse, or an elephant, and I can kind of give it a random kind of local texture, and then the local texture is not able to tell me what's the global structure. So again, this is similar to when we were looking at the beach and the digits. And in the case of textures, sometimes if I'm just trying to classify the texture, this is enough to give me the right label and to learn the right label. But if the task is to classify the different types of animals, and I just look at this texture, it's not enough. So in general, we need to be able to have in our neural networks the ability to look at different resolutions, this multi-scale representation, so that ideally it can learn it by a gradient descent to what to pay attention to and kind of compose different features at different resolutions. So this is a multi-scale compositional prior. So this is also what CNNs do. Basically, you have normally, I mean, it depends on the architecture, but normally you have like the same kernel size. So for instance, a 3x3 type of kernel, but then you have like a pooling layer that kind of downsamples the image. So if the, so if basically we downsample the image, the same kernel now, in the lower resolution grids capture more of the global structure. So this is kind of what CNNs are doing as well by having these pooling layers. They're going to have these different types of activations that capture different resolutions, and they are able to combine all this information to make better predictions. So this is kind of a multi-scale compositional prior, which again can be classified under geometric priors, right? It's kind of playing with the geometry. So this is a bit of an overview. The other part of the geometric deep learning blueprint that we're going to use So we've looked before at equivariance and invariance. Now we're looking at this multi-scale compositional prior, in which we have the original space of signals, right, on a geometric domain, and then we can apply some kind of nonlinear coarsening or pooling operation to map it to a coarser domain where the dimensionality is lower. And then we have some nonlinear function. So in the end, when we look at the overall blueprint, we're going to use this tool combined with equivariance and invariance to construct our neural networks. So, okay. So basically, as we said before, we want to kind of restrict the hypothesis class of our neural network, and then we have a list of desiderata or different recipes that we're going to use. So we're going to use the group invariance, and then the multi-scale structure. And ideally, we want to do this without kind of penalizing the expressivity of our neural network. Because we can be invariant and be multi-scale, but then if our neural network is not able to learn a complicated enough function or an expressive enough function, then this is not very useful because it doesn't allow us to actually model the underlying function correctly. So basically, we have this linear group invariance, right? The problem with linear group invariance is that to be invariant, for instance, to translations of the image, we end up, are not expressive enough because they depend on the group average. So in case of images and translations, it would amount to using the average color. So if we translate, for instance, this is a function, a linear G invariant function that results always in the same output, right? We can translate the image, and as long as we take essentially the group average, we always get the same output. The problem is this is not very expressive. This doesn't allow us to construct very complicated functions. So in general, in neural networks, we want to have like a lot of layers that are able to generate very non-linear and complicated functions. And if we choose something that completely restricts the hypothesis class, then we have a bit of a problem. So we're going to try to be kind of smarter about this. But if we look at kind of the layer level, we can have linear G invariant transformations. So for instance, convolutions in CNNs, what we saw with the 3 example before. And we can have, for instance, in message passing in GNNs, they are also equivalent to permutations. Now, the idea is like, how can we take these transformations and combine these linear equivariant transformations with linear invariant functions? So in general, the problem that you have that if you use these G equivariant linear layers and stack one after the other, and in the end you add an invariant linear layer, you end up with just invariant, the equivalent of a linear invariant. Why? Because basically linear transformations, when you compose linear transformations, is equivalent to another linear transformation, right? And then when you restrict the output to be invariant, doesn't matter if the input is equivariant, you end up with the same property. So this kind of collapses, all these layers end up being collapsed to some equivalent linear invariant layer. So we want to find a way of having like a more broad hypothesis class, but we are going to try to combine the tools that we've shown before to do that. And in particular, we're going to use element-wise nonlinearities, which are very common in machine learning. So basically, we have like this space of input signals, and we're going to apply a nonlinear function pointwise. So in this case, we're kind of shifting the color scheme. So a nonlinear function could be a ReLU, an ELU, a swish function, which are very typical in modern neural networks. But maybe in the past, people used to use sigmoids, for instance, for hidden layers. So those are all valid nonlinearities. And the thing what we're going to do is we're going to use these linear equivariant transformations with nonlinear transformations to generate basically in the end an overall invariant function, but that is more expressive than just adding linear equivariant transformations. And then we are also going to leverage the local pooling or coarsening that we defined before, and a final invariant layer. Okay, so if we kind of look at everything together, we had the kind of the building blocks that we've discussed, this kind of multi-scale compositional prior, right, of just kind of downsampling the image and looking at kernels that represent different scales in the input. We have these non-linearities that allow us to compose together linear G equivalent layers plus the non-linearities and to get like more expressive invariant functions at the end. And then we have like this equivariance and invariant properties. So when we put everything together, imagine we have our input, right? Then we have some G equivalent linear layer, right? Some transformation. So for instance, in the case of CNNs, was convolving with the kernel. Then we have a nonlinear activation, right? So for instance, a ReLU. Then we have local pooling, which you can do like max pooling, average pooling, stuff like that. So you basically downsample the image. And then you apply this kind of structure multiple times. You compose these transformations. You go again, another G equivalent linear layer, which would be basically convolving with the kernel again, applying another nonlinearity, another local pooling. So this is actually explaining, this is a general framework, but this is actually what, for instance, CNNs were doing in the first place. G invariant layer. So basically, at the end of the day, you use this to construct more expressive overall invariant layers, but you want the overall architecture to be invariant, for instance, to the position of the cat on the image, if you want to classify it. So overall, we can look at different architectures under this principle or this blueprint. So for instance, we spoke about this quite a lot, about CNNs, where the domain is a grid, and in general, the symmetry group that we want to satisfy is the translation group. So the underlying transformations or the convolutions with the kernels are equivariant, but at the end of the day, when we want to do classification, maybe between cats and dogs, we want to be invariant to translations. So we've used these non-linearities, these linear equivariant transformations to get an overall expressive invariant model. Then we can have spherical CNNs. So this is kind of related to what we saw before with the rotations, right? So we want to be we want to satisfy the rotation SO3 symmetry group. And then we can have fancier things, for instance, with intrinsic and mesh CNNs with kind of the domain is a manifold, which is kind of some curved space with locally Euclidean structure. And there's like fancier asymmetry groups that we want to satisfy. Maybe more related to things that we're going to see practically speaking in the notebooks. For instance, we have, in the case of GNNs, the underlying domain is a graph, and the symmetry group that we are satisfying is permutation of the nodes, so we can reshuffle the nodes, and message passing shouldn't be kind of affected by the random or rather than random arbitrary labeling of the nodes. In the case of deep sets, it's similar. We have the domain, we have a set. In this case, the set doesn't have connectivity or local neighborhoods, but we still need to be permutation invariant. And the same happens with transformers, in the sense that in the case of transformers, all kind of time steps, which can be represented as nodes of the graph, are fully connected, and it should be also basically it satisfies, the domain is the complete graph, and then the symmetry that it satisfies is permutation invariant. Actually, in transformers, we don't want to be permutation invariant, because that's why we add positional encodings, to be able to tell apart different time steps, but actually the attention mechanism, or the self-attention mechanism in transformers by itself is actually permutation invariant. So, yeah, and then we can have like other kind of architectures, for instance, in the kind of time series domain with LSTMs and satisfying other symmetry groups like time warp, for instance. Okay, so these are kind of the references for the talk, and thank you very much for your time.
So if you have got some questions, like we can take 2 questions. So do you have anything? Can you please raise your hand? We've got time for 2 questions actually. Okay. So Hikmat, can you please provide the gentleman on the second group?
Actually, the local structure and global structure, I can say, what are the advantages of global pooling over local pooling? You mentioned there.
So, I'm not sure the right definition is like global versus.
You actually converted the local structure of a cat to the global, you can say, overall generalization. What are the advantages of overall generalization over actual texture of the cat, for example? There.
Sorry, can you repeat the question? I don't quite understand the question.
You converted from local actual figure of the actual part of the cat to the overall part out there. So what are the advantages of that over there?
Yeah, so I mean, this is very problem dependent. So the idea is we want to have a neural network that is expressive enough, that is able to capture both local and global features and compose them together and use these features. And then by a gradient descent, it's going to learn to self-organize and use these features however it finds most useful. So this is probably kind of dependent on actually the function that we are trying to learn. So for instance, if we are just trying to learn, let's say, I don't know, you could imagine different types of classification problems. Imagine if I'm trying to just classify between cats, right? Maybe just cat and dog, right? Maybe I only need to look at the global structure of the shape of a cat and that's kind of enough, right? Generally speaking. But maybe if I want to distinguish between different types of cats, I actually need to look at the local texture of maybe how their hair looks, right? To be able to distinguish between different types of cats. So then there maybe local features are more important, but kind of the idea is that you want to have or construct a neural network that is able to compose these multi-scale representations, and then everything is worked out by the network itself when doing gradient descent. But we just want to give access to all these types of features.
Thank you.
Have you got any other questions? Anyone? So this is going to be the last question, and after that we can actually follow up on the item.
Hi, thank you for your lecture. At the end, you said that you talked something about self-attention being a permutation invariant operation, right? So the positional encodings that you introduced in the transformer models, can those be considered as some type of geometric priors that we introduced to preserve the ordering of the different tokens in the input?
So basically one thing is like you can represent just like transformers, the attention operation as something called like attentional message passing, and that in general doesn't care about the order of the nodes, right? So you can kind of represent the time series that you are modeling with transformers, and if you forget about the position encodings, it's basically a fully connected graph. So it doesn't actually know it's a time series, and it just computes the inner product between the features of the different nodes, and that's kind of doesn't care about in which order the nodes were in the first place in the time series. So in a transformer, to be able to actually know at which time step you're at the positional encoding, so then you actually break the symmetry on purpose. Because what you are trying to model is not a graph with transformers, you're trying to model a time series, but the operation, like the actual attention operation, if you abstract it away, it's just like doing attention over a graph, so you want to break it, break the symmetry, so you actually kind of are able to tell apart where each node was in time series in the first place. I don't know if that makes sense. Yeah, thank you. Okay, thank you.